We saw in Lesson 2 that pressure can vary across the surface of the Earth. The understanding and identification of this is very important. By knowing where pressure variations exist, we can make assumptions on the movement of air vertically and horizontally. The types of pressure systems we find across the Earth are principally depressions, low pressure or cyclones, and their counterpart, anticyclones or high pressure. There are features called cols we shall also look at later. The first of the pressure systems we're going to look at in detail is probably the most significant to us: depressions, or as they are more commonly known, areas of low pressure. These will be discussed in two ways. The first will deal in small-scale low pressures, and the second with much larger-scale low pressures. The first of these depressions, the small-scale lows, can be found almost anywhere on the Earth's surface and are created when a column of air is warmed from below. Air lying on top of a warm surface will be heated by that surface through conduction. This air will then become warmer and less dense than its surroundings. This will cause it to rise. The rising air will travel up through the atmosphere and eventually diverge when reaching higher altitudes. The total weight of the column of air above that warm surface has been reduced because it is now comprised of much warmer, lighter, less dense air than the surrounding cooler areas. The result of this is a reduced pressure at the surface. If the surface pressure drops, then the air will naturally be drawn towards the centre of the depression. As this air travels in towards the low from the sides, it too will be heated and rise up into the atmosphere. We can then summarise that in these small-scale depressions, air converges near the surface and then rises. These small-scale depressions are sometimes referred to as heat lows. Now we have seen what the airflow is doing inside these lows, let's briefly look at what the weather conditions might be. Let us consider a parcel of air. As it rises, it will expand. This is because the pressure of the surrounding air is falling. Less resistance is therefore offered against the walls of the rising parcel. This expansion will make the rising air cool as it ascends. The process is called adiabatic cooling and will be covered in detail later on. If the air is cooling as it rises, then condensation may take place when the air temperature reaches dew point. These water droplets can be seen as clouds. The clouds that are created will take on a vertical appearance as the air is rising. We call these cumuliform type clouds. Cumulus clouds tend to give showery precipitation, as opposed to continuous precipitation. The type of precipitation is usually rain, and sometimes hail, because they tend to be heavier than the force of the rising air, and will therefore fall due to their own weight. What we will look at now are the problems that pilots may experience when encountering such systems. We have so far seen that the weather has been created from the rising air. However, it is a little more complicated than simply this. If we look at the airflow surrounding the system, we can see a recirculation of air, and outside the cloud, we can identify descending air. This is further complicated when precipitation is falling. The precipitation will drag air with it and cause downdrafts within and underneath the cloud. These up and down drafts, both within and surrounding the cloud, can be a potential problem to aircraft. If a pilot were to fly through these systems, the aircraft could be exposed to significant amounts of turbulence. The stronger the depression, the greater the potential for turbulence. The symbols used to report turbulence are shown in the animation sequence. Another phenomenon significant to pilots is icing. This is where liquid water, or supercooled water, freezes onto an aircraft's frame. This dramatically affects the aircraft's performance and flying capability. Don't panic though, it is discussed in much more detail later on. Let's go back now to our small-scale heat low. If the aircraft was flying through this weather system above the freezing level and liquid water was present, it could lead to aircraft icing. These low pressures involve very active uplift, allowing significant vertical support. Therefore, huge quantities of large supercooled droplets can be suspended within the cloud. It is the combination of significant quantities of water droplets and a temperature of 0 to -15 degrees centigrade that gives the icing risk. As operators of aircraft, we need to be aware of the potential for moderate to severe icing conditions in cumuliform cloud. The symbols for reporting icing are shown in the animation. One other important weather situation is the horizontal visibility near the Earth's surface. If we know air is converging and rising, then surely any impurities near the surface will be drawn up into the upper atmosphere, leaving much clearer air on the surface. We can generally say that in a small-scale heat low, the surface visibility should be good, except of course when there is precipitation. So far, we have stated that these types of depressions are generally on a small scale of maybe tens of miles. However, under rare circumstances, these depressions can become the largest, most powerful and destructive weather phenomena on the surface of the Earth. These are called tropical revolving storms. They are known more commonly as hurricanes, cyclones or typhoons. They can be over 700 nautical miles wide. Because of their scale, the spin of the Earth becomes important. The winds are deflected as they enter the centre of the depression, causing rotational speeds up to 200 miles per hour. These unique depressions will be discussed much later on,